Hello, y'all. Welcome to lesson 4. We're starting the nuclear atom structure 1.2. Our guiding question for this section is how do the nuclei of atoms differ? Well, before we get into that, we have to first learn about the nuclei of atoms. So we're doing structure 1.2.1. Atoms contain positively charged dense nucleus composed of protons and neutrons. Call those nucleons. Negatively charged electrons occupy the space outside the nucleus, so that's what we are covering today. We're going to use nuclear symbol notation to deduce the number of protons, neutrons, and electrons in atoms and ions. We'll cover that towards the end, or maybe even in another lesson. And we're going to make sure that we know that relative masses and charges of the subatomic particles, and we should not need actual values as those will be in the data booklet. And lastly, the mass of an electron will be negligible. So we'll talk about that as we start with our lesson. So I call this atomic theory and structure. You don't actually need to know atomic theory for the DP exam. However, there was a test question on atomic theory this past exam, May 2025. So we're going to cover that one in a little more detail. So let's just start with a brief history of of the atom or atomic model, actually. So the first thought of the atomic model we generally attribute to Democritus. Democritus. I may be spelling names wrong, and I don't really care. Democritus, maybe? I don't know. Doesn't matter. Democritus said things are made up of atoms. So he said everything is made of small and indivisible things called atoms. Basically, if you took some shape in the examples, I believe it's a seashell, so I'm going to try and draw a seashell, and you cut it in half, and then you cut it in half, and then you cut that in half, and then you cut that in half, and then you cut that in half, and you cut that in half, and you keep cutting into smaller, smaller, smaller pieces. Eventually, you get something so small it can't be cut, and that was an atom. It's the building block. And Democritus is kind of right. We do consider atoms indivisible, but we also know they're made up of other particles. So before we figure that out, we kind of move on to Dalton. Now, Dalton had his billiard ball model, and he said atoms are spheres. Atoms are spheres. And then he said that all atoms of the same element are identical. And while they're pretty identical in properties, they're not technically exactly identical. He also said they combine, I'm going to just make this a little clearer. They combine in fixed ratios. Like if you think about H2O, that's a fixed ratio of two H's to one O. All right. Then we start getting to a little bit more detail with, sorry, not Rutherford, not spelled that way, Thomson. Thomson used cathode ray tubes, and he fired a charge or he fired a beam of ionized atoms, and they would deflect one way or the other through a magnetic field. And as those particles deflected, he found that atoms have positive and negative regions. Atoms have positive and negative regions. More specifically, he said it's a big positive mass with small negative pieces. Kind of like a chocolate chip cookie, he called it the plum pudding model. So you have a big positive and a bunch of little negatives dotted throughout. Now, this allows us to see for a separation of charge, so he brought that concept. Then we move down to Rutherford. Rutherford. And this is who the question was on the exam. The exam basically went over his experiment, which was the gold foil experiment. And basically, it goes like this. You have a sheet of gold foil, very thin, and you fire a beam of alpha particles from a little box. And it's a straight beam of alpha particles, which are nothing but helium nuclei. So helium 4 nuclei. We'll get to what that means, but basically, he fired helium-4 nuclei at the sheet of gold foil, and he noticed a couple things. On a big detector around the foil, sorry for this bad drawing, most of the beam went through. Like 98% of the beam, I think, or maybe more, maybe less, I don't know. Most of the beam went through. Most went through. Now, missing some U's and some H. Most went through. Now, a few particles scattered in kind of random directions. And that was confusing to him. But he made a couple conclusions. Number one, he said atoms are mostly empty space, which makes sense. If you're firing a beam at nothing, it continues straight. And so he noticed that the beam mostly went straight, which meant most of the time the beam hit no obstacles. It went right through these atoms, just straight through, like nothing even mattered. But a couple times it went off in random directions. So this is where we'll talk about the helium nuclei. The alpha particle or helium nuclei is two protons plus two neutrons. Protons are positive, neutrons have no charge, so it is a small dense particle. Positive particle. And what would make a positive particle deflect? Well, that small dense positive particle would deflect or repel, whoops, or repel another dense positive particle. And that is the nucleus. So he figured that atoms, whoops, let me get this right. He figured that atoms are mostly empty space with a small, dense, positive nucleus. So we generally see atoms depicted in media as kind of this diagram, and I like to think of that as the Rutherford model, because we have our very dense nucleus in the middle. It's positive, so I'll use some red. And then out on the end, we have little electrons. Now, these electrons stay at different energy levels, which comes about with Bohr. But this is the big conclusion. The atom is mostly empty space with a dense positive nucleus in the center. And so that's the Rutherford model. And that's the biggest breakthrough we really had. We're not going to cover Bohr. We're only going up to Rutherford in this example. So with that, let's talk about atoms as a whole, as we know them now. So atoms are the smallest particle of an element that retains the properties of that element. So that's the same definition we had in 1.1.1, but it's a small particle that still retains the property. So an atom of copper has the same properties, the same boiling point, melting point, density, all that stuff as a sheet of copper. Furthermore, we say they are made of three subatomic particles. So we need to know these particles and we need to know a little bit about them. So we're going to make a little chart. Particle, symbol. So how do we notate it? The charge and the location. So these are the four things that we need to know about each of our particles. So our first one is the proton. Protons are represented as a P with a little plus sometimes to notate its positive charge. You can also notate it as P11. Its charge is positive. Oop. And we actually missed one thing, so I'll have to scooch it all over. We also want to include relative mass. We'll talk about relative mass in a moment. Its relative mass is 1, and its location is the nucleus. Up next, we have our neutrons. Neutrons are represented, not with a P, with an N and a 0 for the charge, or N01. Its charge is nothing, neutral. Its relative mass is also 1, and it's also in the nucleus. Together, protons and neutrons are called nucleons as they're particles that are in the nucleus. Last, we have electrons. Electrons are represented with E minus, E10. They have a negative charge. They have a relative mass of 1 over 2,000. They're about 1/2000th the mass of a proton or a neutron, which basically means they're negligible. So whenever we're considering mass, we kind of ignore the mass of the electron because if we have one proton, one neutron, and one electron, the mass is 1 or is 2 about, and that's close enough. And this is in the energy, in the energy levels around the nucleus, sometimes referred to as the electron cloud. So, along with these particles, we need to know a couple things about atoms. When we refer to an atom, we say atoms are electrically neutral. What that means is that we have the same number of protons as electrons. Because protons are positive, electrons are negative, their charge cancels out. The charge cancels out. So if we have 12 protons, then we also have 12 electrons. That's 12 plus and 12 minus for a total charge of 0. The thing I'm referencing right here, by the way, is sorry, I was going to say carbon, but 12 protons is actually magnesium. Uh, Carbon 12 is 6 protons and 6 neutrons. This is magnesium. All right. Now, with this, we have a new notation that we have to learn that includes protons, neutrons, and electrons. So let's learn about nuclear symbol notation. This is something that you're going to see quite often, and you should be able to write as well as read. So whenever we see an element, it generally will look like this, where X is going to be our element symbol. A is going to be our mass number. Another word for the mass number is nucleon number, which tells you a little bit about what mass number is. If it's nucleon number, it's the number of protons plus neutrons. In other words, it's the number of nucleons. Z is our atomic number. In other words, it is the number of protons. Now, the atomic number is very, 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 very important because the number of protons identifies identifies the element. If we have 6 protons, that is always carbon. Always, always, always. Carbon always has 6 protons. No more, no less. One less, and it is no longer carbon. One more, and it's still no longer carbon. So, nuclear symbol notation is very important because it tells us a couple things. So let's go straight into some examples. If we look at iron 54, this is another way of writing it. This is our element, and this is our mass number. So the way we could write iron 54 with atomic symbol notation is Fe, which is the atomic symbol for iron. It's our element symbol. 54 for the mass number, and iron has 26 protons as found in the periodic table. If you look at iron's spot on the periodic table, you'll see Fe with a 26 above it. That's our atomic number. So this is how we would write iron 54 in atomic symbol notation, or sorry, nuclear symbol notation. It tells us exactly what we need to know about our nucleus, the number of protons, the number of nucleons in total. Something else about this is because this is an atom, we can calculate electrons. We do this by just taking our mass number minus our atomic number. Or sorry, whoops, whoops, whoops. Sorry, I meant calculate neutrons. We take our mass number minus our atomic number. Our mass number is 54, our atomic number is 26, so we get a total of 28 neutrons. And we know that because, as we said before, our mass number is protons plus neutrons. So 26 plus 28, 26 plus 28 equals 54. Now you might have said, wait, what about electrons? Because you did mention that, and we can still calculate electrons. Electrons. It's very simple. It is the atomic number as well. So there are 26 electrons. And I know that because we're looking at an atom. And as we mentioned before, atoms are electrically neutral. The protons equal the electrons. The last thing I'm going to end on is this is not always the case. If protons do not equal electrons, we call that an ion. Ions are things that have a charge. So a very quick example might be sodium ion. The most common sodium ion is represented as Na+, meaning that it has one more proton than electron. So in that case, normally sodium has 11 protons and 11 electrons. We have one more proton. So there are two ways to have one more proton. We could possibly say that we have 12 protons and 11 electrons, or we could have 11 protons and 10 electrons. Now, you have to figure out which one is correct. Well, we have to go back up to what we said before. The atomic number, the number of protons, identifies the element. And we remember that 6 protons is always carbon. Therefore, 11 protons is always sodium. And therefore, this is incorrect. 12 protons is no longer sodium. So that's our answer. So sodium ion has 10 electrons. All right. That's all we have today. Have a great day.